Okay, welcome back to the P-Dog channel. This is P-Dog, and we're going to start chapter 23, studying nuclear chemistry. And we start with nuclear radiation and how it was discovered. Radioactivity was discovered by, you don't need to see that. Radioactivity was discovered by Henri Becquerel, who is this guy right here. And let's move him to the front. And he was the first person to discover radioactivity, and he did it. Now, first of all, the first thing with Becquerel is check out the chin here. That is epic. With the part in the chin, the part in the beard, that is ridiculously cool. Okay, so that's Becquerel, and Becquerel discovered natural radioactivity, which is the emission of particles from the nucleus. He discovered it in 1896 from uranium salts. Now, think back for a second. What else was discovered in 1896, if you remember from the previous chapter? Okay, previously, what was discovered in 1896 was the electron by Thomson. Capital T for Thomson. Thomson discovered the electron in 1896. And so all this was happening, the working with the nucleus of the atom and subatomic particles began right around the turn of the century. Anyways, he found natural radioactivity coming from uranium salts. And what happened is he took this uranium and he put it into a closed drawer and put it with photographic film. And his the salts caused photographic film plates to become fogged without any sunlight and moisture. Normally you need light or some sort of energy to defog the plates, but it didn't come from anywhere, and so it had to have come from the uranium salts that he happened to put into the drawer with the photographic film. Okay, so Becquerel discovered it. Then we have the husband and wife pair of Marie and Pierre Curie, and that's these two. They are actually on the formerly French currency, but the French don't use francs anymore. This is a 500 francs, 500 francs. But this is a non-existent currency anymore because France is on the euro. But they were honored with the money because they were such important contributors to science. Marie and Pierre Curie were a husband and wife team that were two of Becquerel's associates, and they isolated and purified two new highly radioactive elements: radium, because it was radioactive, and polonium, which was named after Marie's home country of Poland. Marie Curie named the process where materials give off rays, and she called it radioactivity. And she won 2 Nobel Prizes for her work, one in physics and the other in chemistry for her works in radioactivity. One of the sad things, however, is that Marie Curie is almost certainly the first person to have passed away from some kind of radiation poisoning. She passed way before her time, dying of acute leukemia, which is almost certainly due to her working with radioactivity, because they did not know that the radioactivity would actually alter their DNA so much, because they didn't know about DNA at the time. DNA wasn't discovered until the 1950s. Okay, they also work with radioisotopes, and these are the nuclei of unstable isotopes that gain stability by emitting radioactive particles. Now, there's 3 types of radiation. 3 types of radiation emitted from unstable nuclei. The first is alpha, okay, which is given by this Greek symbol of the alpha. The second is beta, and it has its Greek symbol B for beta, with a little tail at the end. And finally, gamma, which is that one, which, yes, has the same name as the radiation that caused the Hulk to turn green and altered Bruce Banner's ability to, rage and, turn into a green rage monster. But that's fiction. Gamma rays, however, are not fiction, and they are deadly. Ernest Rutherford discovered 2 of these particles, emitted by radioactive elements. He discovered the alpha and beta particles, and all of these emissions come from the nucleus. Now, an alpha particle is a high-speed helium nucleus. It is composed of 2 protons and 2 neutrons with a +2 charge emitted from an unstable nucleus. Now the symbols for it include that little alpha right there, an He +2, or 4,2 He. And sometimes we might even include the and sometimes you can throw in there the He plus +2 to go with that. Okay, alpha particles are very low penetration. They're stopped by paper and clothing. They move at about 1/10 of the speed of light. 0.1 c, which is still very, very fast. That's 16.8 thousand miles per second. Very, very fast. And there's an equation. So alpha decay equation. When a particle when a nucleus gives off an alpha particle, it has a mass number that is 4 less because of 2 protons and 2 neutrons, and an atomic number that's 2 less because of the same 2 protons. So for example, if a uranium-238 isotope gives off an alpha particle, it will result in a decrease of 4 in the mass and a decrease of 2 in the atomic number. So that's an alpha decay, and we'll get more into that later, and more into that with our practice. The next kind of decay is a beta particle. A beta particle is a high-speed electron emitted from the nucleus. Let's get this up here so you can see it. A beta particle is a high-speed electron emitted from the nucleus. It is produced from the spontaneous conversion of a neutron into a proton. And its symbols include the beta. There's usually a minus there for that, because there is another kind of beta. It's usually beta minus. Or 0 minus 1 beta for its isotopic notation. And minus 1 is interesting. We'll talk about that in a little bit. Or 0 minus 1 E, because it is an electron that is emitted from the nucleus. Now, you may be asking yourself, I thought electrons went around the nucleus. How could they possibly be coming from the nucleus? Is an electron emitted from the nucleus? This actually occurs when a neutron decays into an electron and a proton, conserving the amount of charge. Electrons have medium penetration, meaning they can pass through paper, but they're stopped by anything thicker than that, aluminum foil or thin wood. They move at 9/10 of the speed of light. So we're talking at about 150,000 miles per second. It's moving really, really fast. And here's its equation, and this one's a little different. It's a new particle. It has the same mass number because electrons have 0 mass number, but it adds an atomic number because the process of a neutron turning into a proton will create a larger mass number. So a 14,6 carbon atom will become a 14,7 nitrogen isotope when it loses a beta particle. Now, there's a decay series, and this is how all of our elements actually get made in the universe. Particles usually do not become stable in a single decay event. It requires a series of steps for the particles to become stable. Now, the uranium-238 decay series starts with a series of alpha and beta decays in order for this radioactive substance to become stable. And it turns into lead-206. So, what would happen if U-238 undergoes the following decays? So this would start with 238-92 uranium, and then undergoes an alpha and a beta and a beta and an alpha 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 and a beta and a beta and an alpha and a beta and a beta and an alpha. So I want you to pause here and work all these out. and what they all become. And we will continue. You should continue after you finish that. And here's an extreme close-up of what you should have got right now. Notice all of these are the mass numbers, and those are the atomic numbers until we get all the way to 20682 lead. Okay, so let's zoom back out. And so let's focus on what happens to the mass number and the atomic number at each step. Each time you have an alpha particle, the mass number subtracts 4 and the atomic number subtracts 2. Each time we emit a beta particle, the mass number doesn't change, but the atomic number adds 1. So what happens is the mass number is a total change of minus 32, and the atomic number changes by 10 over all of them. Okay. Which brings us to gamma particles. Gamma particles are electromagnetic waves that with a wavelength shorter than X-rays. They're very short. Okay, the symbols for these include gamma or 00 gamma. Okay, and gamma particles look like, well, this is where they fit in the spectrum. So let's okay, here's visible light. Gamma rays are way over here. When it comes to their wavelength, and they're very high frequency, very long, very short wavelength rays over here. This is what we can see, and there's a whole bunch of other funny stuff in here if you want to take a look at those. This is where they fit. And this is how they all penetrate. This is how all of our particles penetrate various things. And it's important for us to understand that alpha particles penetrate, they hit your skin, but then your skin absorbs them. But because it absorbs them, it's very damaging to your skin. Beta particles will pass right through you, and the aluminum foil can stop them. Gamma rays go through aluminum, but they pass, and lead will block them off. And neutrons will actually penetrate through lead and get stopped at concrete. And neutrons are a very penetrative particle. So the highest penetrating particles are the gammas, aside from the neutrons. And they're partially shielded by concrete. It is a particle of light, an electromagnetic particle that travels at the speed of light. So its speed equals the speed of light. Its mass number is 0, its atomic number is 0, and no new particle is formed from gamma radiation. It usually accompanies alpha, beta, and other forms of radiation. Gammas are the most damaging form of radiation in tissue because they pass right through the body, changing chemical bonding in DNA. And there are no nuclear equations for gamma decay. There's nothing that changes in the nucleus. And then finally, we have the deflection of particles, okay, which is dependent upon mass and the charge of the particles. And we saw a lot of those with the cathode ray tubes and the anode ray tubes, and how magnetic fields will affect how beta particles move and how alpha particles move, but they won't affect gammas. So that's it for 25.1, and this is P-Dog signing off.